Okay, so let's finish this lecture with an introduction to deep convolutional neural network. So at this point, this lecture, in last week's lecture as well, we assumed that the patterns were organized in terms of feature vectors. And the form of these features were specified by the user or the human designer. And this had to be extracted from images prior to being inputs to the neural network. We've seen in the practical this week an example of that with the banknote data set, right? The banknote data set where the input were pattern vectors that were extracted by traditional image processing tools. A convolutional neural network doesn't need these predefined feature vectors. The inputs to a convolutional neural networks are images. And somehow, as we are going to see today, these CNNs, these convolutional neural networks, they learn the features, as well as the classification of the images. We're going to see the Linnet architecture. It's well described in the book, which, because it's simple to understand, it works as a good introduction to convolutional neural networks. And the derivation of the backpropagation equations are straightforward. These are the differences between a CNN and what we've just seen. It's the fully connected neural network that we've just seen. First, as I said, the inputs to a convolutional neural networks are to the arrays, images, whereas the inputs of the are vectors for the fully connected neural network. The convolutional neural network is capable of learning 2D features directly from raw data. That's the main advantage. And in particular, on a convolutional neural network, we feed into every input of a layer a single value that's defined by the convolution. We've learned convolution. That's basically what I don't think that I had one lecture where I didn't mention convolution. Yeah, convolution, the stuff that you've done for assignment 1. It's a convolution over a spatial neighborhood in the output of the previous layer. All the rest is very similar. It does a sum of products. It uses a bias value. The result is passed through an activation function. The activation value becomes a single input to the following layers, and so on and so forth. That is the architecture of a basic convolutional neural network. We're going to see this step by step. We're going to see this step by step. Let's otherwise I'll keep repeating myself. The type of neighborhood processing in a neural network is spatial convolution. It computes a sum of products between pixels and a set of kernel weights. Remember, right? The convolution is nothing more than a sum of products. A neural network, the main process of neuron is what? It's a sum of products. So this was a great idea that these people had back in the 80s, is that, well, they're both doing sum of products, but a convolution, what's doing is somehow extracting features from the images. It's extracting lines, points, isn't it? We've used convolution for a number of things, for extracting a number of things. And the neural network is doing this just some of it from stuff that were not directed for finding features. If we combine both, then that's the great gain of the convolutional neural network, is combining the power for feature finding that convolution has with the power of learning parameters that the neural network architecture has. And what are the parameters that the convolutional neural network learns? Any guess? From the two people that are in the room. No, I don't want to try. The parameters are the kernels, the convolution kernels. It learns the convolution kernels. It learns the values of the kernels. So that's basically what it does. The neighborhoods, and of course, they have to change the names just to make things more difficult, right? Instead of calling it an image, a neighborhood in the image we've been calling it for donkeys of years, they now use receptive fields. So a receptive field is just a neighborhood where we are passing a convolution filter, right? In the deep convolutional neural network literature, they use receptive fields for the image resolution. And these receptive fields move over the image, executing convolution. Move over the image, executing convolution. The set of weights arranged as a receptive field is a kernel. The number of spatial increments, I've always talked about a convolution that you do spatial increments. And in convolutional neural networks, there's a called strides. Honestly, I don't know why they changed the terms. It's just spatial increments of a convolution kernel. So each convolution value, we add a bias, then pass the results through an activation function. In the same way, the activation functions are pretty similar, are those that we've learned from the neural network architecture, especially the reload. Because usually these convolutional neural networks are very deep. So the reload sorts out the gradient vanishing problem. This value then, that we pass the convolution, is fed to a corresponding X and Y location in the next layer. And what's going to be the next layer like? It's going to be other images that will be the result of convolution on this image. So if I have, in this case, there are 3, and of course, these images then they change the name. They are not images result of convolution. They are feature maps. Feature maps. Okay. So in this case here, this example, there are 3 convolution kernels. They are generating 3 results, which are 3 feature maps. And the role of convolution here is to extract features such as edges, points, blobs, as we've seen. Convolutional layer, that's 3 feature maps obtained from 3 distinct kernels. Then we've understood the input, past convolution, 3 kernels, 3 feature maps. The kernels, there is the added bias and activation function, as in the neural network, to generate these 3 feature maps. And now, at this stage, there is something that we call, that's called subsampling. Subsampling. So what subsampling does is, or pooling, also you're going to see pooling. What subsampling does is it reduces the dimensionality of the data. And it's also called a pooling layer, where it's this data, if we become a data of an image of less dimensionalities, a reduction of spatial resolution. And they say in the literature that's responsible for translational invariance. But I do think that the main reason for having this pooled layer is to reduce the volume of data. Because if I have a very complex set of images, I'm going to have many convolutions, many convolutional kernels. And basically, I'm multiplying the data set, which is also big, into a bunch of other feature maps, which are the results of this convolution. It's convolution processing. Then I do subsampling to get the result more manageable. And this is done by subdividing the feature maps into a set of small, typically 2 by 2 regions, which are the pooling neighborhood. So each region here, the pooling neighborhood, is going to generate 1 point in the next stage. In the next stage. In the next stage, again, I can pass another convolution with another bias and activation, generate a number of feature maps. In this case, I have 1, 2, 3, 4, 5, 6, 7 feature maps, meaning that I have 7 convolution kernels, each one of them generating a number of, generating a new image from these pooled feature maps. Again, subsampling, pooled feature maps again, see the dimensionality. But in the end, what I want to do is classification. So this architecture here doesn't do classification. What does classification? It's the fully connected neural network. So at the end of a convolutional neural network, I have a fully connected network where this bunch of feature maps here, which are, in a sense, it is like an automatic analysis of the initial image, extracting the features. They should be vectorized because there's a fully connected neural network where the input should be a vector, a feature vector, and the output will be a bunch of classes. Will be which class this input image is. Okay. There is a number of common pooling methods. We can get this little region. Sorry, this should be the region, the pooling network, and substitute this network, this 2x2 region in the image by the average. That's one method, or by the maximum value. That's the max pooling, or by the L2 pooling, substitute by the square root of the sum of these pooling network here to generate this dimension feature maps, which are called pooled feature maps. Convolution gives you filtered images. Pooling gives you filtered images of lower resolution. The feature maps in the first layer become the inputs to the next layer, which is represented here. But now we have multiple pooled feature maps. All right, that's important. So with the multiple pool feature maps, they are combined into these next feature maps by just superposition, because these are all linear operations. I can just combine those by superpose those. And as the ultimate goal is the classification, the final pool feature maps are fed into a fully connected network in the same way that we've seen before. So an example, then you can imagine that this is the receptive field. Think of each element of this 2D array here as a neuron. The output of these neurons are pixel values creating the feature map. So that's the convolution. Imagine that the convolution is the input to a neuron, and your neuron is going to output a value that's a picture, that's a pixel in the feature map. The neurons in the feature map of the first layer have output values generated by convolving, as I'm saying, the image kernel whose size and shape are the same as the receptive field. And that's important. So the coefficients of the kernel are learned during training. To each convolution value, we add a bias and pass the results to an activation function to generate the output values of the corresponding neuron. The output values of neurons in the pooled feature maps are generated by pooling the output. That's everything that I've explained, right? And that's one example. So if I have this image here, the first feature map, for example, would be that by using this kernel. This feature map is applied by convolution, convolving this kernel, and that's the result of the pooled feature map. It's the same image but with a lower dimension. And you see that this kernel is represented as intensity values. And intensity values, you can understand this as a weight, right? Each point here of the kernel is a weight that is learned by backpropagation. A similar process to the one that we've seen before for the fully connected neural network. Well, that's just an example of the whole architecture applied to this image. And at the end is the same thing that we've seen in the fully connected neural network. We're going to classify this as the number 6 because number 6 received the highest value. The neuron representing number 6 received the highest value. So these are these are basically given this architecture here. You see that there are these 6 feature maps. At the first layer, this is what the convolutional neural network learned as the feature maps, obtained as the feature maps. So you can see that these are. It's hard to interpret, but you see that there is something that a kind of what this neural network is learning is pieces of numbers, right? And that is the feature maps learned at this stage here. This is the feature map of the second layer. These are very difficult to interpret, so you can't see anything from it. It's very surprising that it has such a good good impact. But if we look at this this example here, so this is the input, the feature maps given this input, you see that this 6 here, this feature map represents some sort of foreground, background of this number. This one learned some sort of blob feature, or that this part here is more blobby than the other parts. This feature map kind of represents this this wiggle here, and this feature map is this kind of loops. And this is just a pooled feature maps, just a smaller dimension of the feature maps. On the next layer, basically can't make heads or tails of what these feature maps are, but sort of pieces of the images. So you see this piece here is represented by this feature map on the second layer. This kind of feature here is represented as this feature map in the next layer. And this is the vectorization of these the pool feature map of this part here. The last pool feature maps are vectorized, and then the neuron that fires with the highest value is the neuron that I'm gonna assume as the class of that. The computation, the mathematical derivations for this is on our book. I do recommend you to read. It's basically very similar to the computations that we've done for the fully connected neural networks, but with an extra complication is that I have to take into account the convolutions, and the convolution is again a sum of products. So the derivations basically takes into account all of this sum of products, and in the end, the steps of the algorithms are pretty much very analogous to these algorithms used in a fully connected network, where you have a bunch of input images, a forward pass, which is, look, this expression is exactly the same expression as we've seen before, but instead of having a sum of products, I have here a convolution with respect to a kernel. In the backpropagation, is adjusting these kernels, the values of these kernels, given the value of the errors in the end. Of course, there's a little complication here that it gets this kernel should be rotated to 180 degrees for the reason that we're actually going backwards in the network. But the maths that leads to this is quite interesting, and the only thing that it uses is the chain rule that we are from calculus. And then the update of parameters. This is the updates for the kernel. Notice that here I have also a matrix, because the kernel here is a matrix. And same thing, I have to double summations here for the bias, because I have to take into account the receptive fields of the images. This is a simple example of teaching a basic neural network with 2 feature maps, with 2 kernels, 2 convolution kernels, one pooled layer to learn simple images. These are the input images that are given to this network, and these are the training set. You see that the kernel, the kernel that the network learned by backpropagation and the bias here, they look pretty much like the same way that of the weights that have been learned that we've seen today as a result of the learning process of a fully connected neural network. But in this sense here, this is not the weights of the neurons, but these are the kernels of the convolutional neural network, right? And as evaluating that by mean squared error gives you actually, when I looked at this picture, I thought, well, it's not a great learning rate, but the book says perfect recognition of training and test sets were achieved after approximately 100 epochs, despite the fact that the mean squared error was relatively high there. But the book doesn't explain that why it got the perfect recognition of training and test sets. I think his training set was biased. Honestly, I do think his training set was biased. So you don't get a perfect recognition with this kind of curve. We're going to see next week. We're going to run that in Python at this same time next week on Wednesday. This is the MNIST data set. It's a data set of 60,000 training images of handwritten digits. It's been used from this 60,000, 10,000 were used as test images. These are gray images of size 28 by 28 pixels. The book used this architecture with 6 convolutional kernels, 1 pooled layer, then 12 convolutional kernels, and on a second convolutional layers, and then the vectorization here to get the proper outputs. Don't ask me why 6 feature maps and 12 feature maps here. It's try and error. I had students in the past making big tables of the kinds of layers that they used and the recognition rate at the end. This try and error, and this was a good result, right? So the mean square error is it converges really fast in terms of even here at with 4 epochs, you have a great training accuracy as well. And so training accuracy after 80 epochs was near 99% of accuracy. And you can see this by class. For each digit number, we have a very high recognition rate. From the number 5 was a little bit rubbish, but 99% is a great recognition rate. This was for the training set, and this was similar to the test set. On the test set, the number 6 was badly recognized. But badly, we're saying above 98%. That's a great recognition rate. And these are the kernels learned during this process. I've shown this already, right? This is the result of a forward pass. This is the feature maps obtained, the pooled feature maps, and the feature maps learned in the second layer, and so on. Right. So let's play with this. Let's play a little bit with this. This is a wonderful visualization as well. Discard everything. We're almost at the end, people. Where are you? Okay. So let's visualize a convolutional neural network, how it works. So let me write here a number 7. So this network had what 1, 2, 3, 4, 5, 6 convolutional layers. You can see that each pixel is coming from a particular position in the image. This is the convolution working for you. So a particular region convolving with this kernel gives you this kind of feature map, right? This is the pooled variance. You see that's a 2 by 2, from a 2 by 2 region here in the image, in the feature map, generating 1 pixel in this pooled image. Same thing for every one of them. And this actually is combining, as I said. So as we have a bunch of feature maps, all of these feature maps are combined. The results of all of these are combined into one to pass through this this new convolutional layer. And this again is the pooled layer, and this is the vectorization of these results. This gives you then it has one hidden layer. That's the fully connected neural network, and in the end, the first guess was a 7. It's the the brightest value here was 7. The second brightest value was 3. It sort of looks like a 3. Let's try to mock it. If we say this, yeah, it recognized as a 3. Was very good. Recognized as a 3. You can play with this later. You can do loads of stuff with this visualization. I really enjoyed it. I spent many times, many hours, well, not hours, but quite a lot of time playing with this today. All right, so I don't know why I came so backward here. Let's see, we're talking about convolutional neural network and the MNIST data set that we're going to run next week. Are you MNIST data set? Here you are, MNIST data set. You can play with this. And finally, let's learn some cat and dogs. That's a more difficult, more complex data set. It's also freely available and also used as benchmark, where we have a bunch of images from airplanes, a bunch of images of automobiles, a bunch of images of birds and cats and dogs and frogs and horses and trucks and all sorts of stuff. We use the same architecture as used in the MNIST, exactly the same architecture for the convolutional neural network that we used before. And of course, the mean square error for this case was terrible. The training accuracy was around 66%, not very good at all. 60% of accuracy. How can you get it better? How can you make it better? More complex network. That's one thing. How complex it should be. Try and error. Just keep building layers as we've been doing, playing around in the previous visualization. Different pooling strategy, more training examples, a lot of time to fiddle around with parameters. That's what we need. If we're going to learn, if you're going to apply these neural networks, you need a lot of time for fiddling around with these parameters. And the recognition accuracy, you see that for the class 2 here was quite good. Which one was class 2? Class 2 was cars. It liked cars. 89%, right? The network learned well, 85%. But it was terrible for frogs. Cats and dogs were not very good. It was around 50%. 50%. On the training set. On the test set, it was just terrible. Just terrible. Then you can see examples of the kernel. These are on the book. And how the kernel analyzed it. The feature maps came from the airplane. Then the pooled feature maps, the second layer, pooled feature maps of the second layer. And the neural network output as class 1, which is the class of airplane. This was an example where it got it right. There's a bunch of reading here. I just got this message with this This is a great blog towards data science. Please read that. It's not one thing that you're going to read in 1 hour. It's going to take you a couple of hours to read. But there is loads of information about bias and the various definitions of bias that you get. I think it's worth having a look at least at this initial. There's a bunch of articles. It's not only one, but what is AI bias? You should read that. If you have 10 minutes of this week, read that. So there's distinct definitions for the word bias in data collection, cognitive psychology, neural network algorithms that we've seen today. That's just the intercept term. And they say that bias sounds cooler than that high school math word, right? That may be the only reason, and then so on and so forth. Please read that, at least this one, because we make a big mess with the word bias. And finally, ladies and gentlemen, the end. We've read the whole book. Congratulations. I hope you've enjoyed this. And there's still one thing that I want to do with you. It's to run the MNIST dataset with a convolutional neural network next week on Wednesday at 3 o'clock on Collaborate. I'll make sure I'll record it. Maybe I'll run MNIST, and maybe I'll run also the other cats and dogs dataset as well, so that you have a feel about applying these ideas. And congratulations, you've done it. Thank you, people, and hope you've enjoyed, and I'll see you around. Bye.